I wanted to make a video here to kind of clarify a little bit about which regression model to use and positive and negative correlations, linear correlations, and non-linear correlations. So I'm going to begin by looking at positive linear correlations. So for positive linear correlations, your R value will be positive, and your data will look like a straight line that's going up, because if you remember, we talked about a positive correlation, meaning as one increases, the other increases. This would be a moderate positive linear correlation, and that's because your R value is still positive, but it's not as close to a straight line. And this would be very weak with R equals 0.16. It's close to 0, so there's really close to no correlation at all, and it's not going to be very useful for making predictions. So if your correlation is coefficient for a linear correlation is between 0 and 0.19, it's very weak. If it's between 0.20 and 0.39, it's weak. 0.40 to 0.59, it's moderate. 0.60 to 0.79, it's moderate to strong. And 0.80 to 1.0, it's very strong, and it's useful for making predictions. So negative correlations, linear correlations, are going to be the same, except in a negative linear correlation, R will be negative, and instead of the line pointing up, the line will be going down, because if you remember, negative correlation means as one variable increases, the other decreases. So let me show you an example of a negative linear correlation. So I'm going to get rid of this line for a minute. If you look at this scatter plot, it looks like a line. So instead of having to try every single, linear, quadratic, cubic, logarithmic, exponential, because that would take a long, long time, you can look at this scatter plot and say, okay, does that look like a straight line to me? Yes, it does look like a straight line. So this means the linear model is probably a very good fit for this data. So notice, if I type in y1 is approximately equal to ax1 plus b, you get that r is negative 0.9872. That's very close to negative 1, showing a negative linear correlation, and that the linear regression is a good model for this data. So what happens is that sometimes you'll have a scatter plot that looks like this. Now, if I'm looking at this scatter plot, that doesn't look very much like a line to me. Okay? So the linear correlation or linear regression is probably not a good fit for this data. In fact, if I type it in, y1 is approximately equal to ax1 plus b, if you'll notice, it says R is 0.165. That's a very weak positive linear correlation, but it's not useful for making predictions. So really here, it's so weak that you would say this scatter plot doesn't look like it has any correlation at all. And why do I say no correlation at all? Well, there's other types of regression models besides just linear, and you have those. Let's see. I can get this open. It doesn't seem to want to open. So you have these in your notes. So if you look, you have an example of negative linear correlation here, but then you have other scatter plots. So if you had a scatter plot that looked like this, it would be a quadratic relationship. If you had a scatter plot that looked more like this, you easily know it's cubic. If you have a scatter plot that looks like this, that's negative, or exponential regression, sorry. And if you have one that looks like this would be a logarithmic. Okay. So if it looks like one of these models that's not linear, you could try one of those models to see if one of those models would be a good fit. Okay, so maybe, you try, let's say you try the quadratic model. Whoops. Squared plus bx 1 plus c. Okay, and so if you look at this, you see at this r squared value of 0.031. Again, that's pretty close to 0, which is indicating to you that this does not really have a correlation at all. So you could try other types of models as well. Now, if you'll notice, when I do this on Desmos, this is quadratic and it only has r squared, and linear has r. Well, that's because when you r is really to describe linear correlations. So when you see r squared, it does not describe a linear correlation. It basically says the closer this value is to 1, because it's always going to be positive, the better this equation fits the data that you have. So it does not describe, your r squared does not tell you whether the correlation is positive or negative. It just tells you how well the line best fits the data. You'll notice for a quadratic or cubic, you only get an r squared. And you'll say, okay, well, if r only describes linear, you'll notice if I do it logarithmic regression on here, for example, or an exponential. So I'll do an exponential one. So if I do y, ooh, nope, let me go down here. If I did y1, it's approximately equal to a, b, the x, 1. So if I do an exponential regression equation on here, you'll notice that I only get an r squared. Again, the number is super close to 0, showing me that this doesn't really have any correlation at all. But you'll notice if you do that on a calculator, so you get r squared here, if you do it on your calculator, you'll get an r squared and an r. And you say, well, r only describes linear correlations. Why is there an r for an exponential and an r for logarithmic? That's because some equations can be transformed into linear data, and that refers, the r value that you see in your calculator will refer to the linear data. But if you're using any other type of correlation besides a linear correlation, you're going to describe your correlation as nonlinear. Okay, so when you have a linear correlation, then you can describe it as positive or negative based on the r value. And remember, positive means as one's increasing, the other's also increasing. Negative means as one's increasing, the other's decreasing. So you can still talk about a positive relationship, but you're not going to say any other relationship is not going to be linear. And really, for any other correlation, your r squared tells you how well that equation fits the data that you have. So if you look at this last equation here, or this last scatter plot, if I'm looking at this scatter plot, from the very beginning, I'm probably going to say, okay, that doesn't look like a line. So if it does not look like a line, if your scatter plot does not look like a line, you're not going to use a linear regression. And if I go back to my notes page, this kind of looks like an exponential regression to me. So I might try, and if you'll see here, sorry, r is 0.71. So it's positive, meaning as one goes up, the other goes up. So there's still a positive relationship here. You can see that. As one's increasing, the other's increasing. It just doesn't look linear. So if I go in here and I type in, this looks more exponential to me based on the scatter plots that I've seen. So if I type in an exponential equation for this particular problem, okay, if you look here at this data, okay, this exponential curve matches to this data really well. And if you look, it says r squared equals 0.9998. Okay, so this is going to be a way better fit for this data than the line. You would not choose linear regression as the best fit for line for this data because the scatter plot doesn't look like a straight line, first of all. And this r squared tells me, okay, this data, since this r squared value is close to 1, is a really, or this equation is a really, really good fit for this line. Now again, your calculator for exponential will also give you an r value and also be close to 1 in this case, but that's because they transform this to a line using some mathematics, to linear data using a bunch of math that we're not going to talk about here because it's beyond what we're doing in this class. But basically this r squared being so close to 1 tells you that this is a really, really good fit for this data. So you're going to look at your scatter plot and use that to determine whether or not you think a linear regression would be a good fit for the data, or if there's a better model. So in this case, you can look at the data and say, okay, this looks like an exponential curve to me. That is a better model for this data.